Hi, and welcome to video 3 of 3 for Chapter 9 material. Now, the last two videos have taught us about the different types of collisions that you can see in general, um, perfectly elastic or perfectly inelastic. And as I said, collisions in general are some combination. They sit somewhere in between the two. Now, remember, one of the issues that we had to deal with when we dealt with elastic collisions was the fact that um, you know, we didn't have enough information if you just go off of using conservation of momentum. So we had to invoke conservation of energy in order to find solutions. So what I like to do today is to start off with an example that involves two-dimensional motion. And as a consequence of this, we have an extra direction, which allows us maybe to get a little bit more information, so we don't necessarily have to appeal to conservation of energy. We may still have to, but just in general, we may not have to. So in this example, we have a cue ball of mass 0.17 kilograms that hits a 9 ball. That's initially at rest. Now, it's going to bank it into a pocket, and the angle that our 9 ball is going to make, which I'm going to call this theta 1 here, is 35 degrees. Okay, so M1 is going to be our 9 ball. It has a mass of 0.16 kilograms. And as you can see, the initial velocity of our cue ball, which we're going to call M2 here, which has a mass of 0.17 kilograms, its initial velocity is 2.5 meters per second along the x-hat direction. Now it hits, this is banked this way, and so we know its velocity after the collision is 3 meters per second. All right, so the magnitude here of, actually that's not v1 naught, rather, that's after the collision, is 3.0 meters per second. Okay, we also know that it's sitting at rest here at the origin, which means that its initial velocity is going to be 0. So what I'm trying to find here is what the velocity of the cue ball is after the collision. All right, so you'll notice here that I have this dotted arrow drawn below the x-axis. And one question you might have is why? Well, if you take a look here, initially we have a ball at rest, and then we have one moving to the right, strictly along the x direction. But after the collision, we have this one moving upwards with not only an x component, but also a y component as well. Now, if you think about conservation of momentum, remember it's a vector. So here, our initial momentum is strictly along x, which means our final momentum is going to have to strictly be along x as well. So if there is upwards motion like this that has a y component that's positive, then whatever the deflection angle here is going to have to be negative in order to have these parts cancel each other out, and at the end of the day give us a final momentum that's explicitly along the x direction. So that said, we know it's going to be below x. We're going to call this theta 2, and this right here is going to be, the velocity that we're trying to find, which we're going to just write as that. So here, if I write out what I've been given, my first mass here is 0.16 kilograms. Its initial velocity is 0. Its final velocity, we know, is 3.0 meters per second, and it makes an angle of 35 degrees with respect to the x-axis. Now, for M2, we know it has a mass of 0.17 kilograms. Likewise, we know its initial velocity. It's 2.5 meters per second in the x-hat direction. Okay? And that's about it. Okay, now what we're trying to find is V2. Okay, so what I'm going to do is to take this image here that we sort of filled out, and we're going to do a before and after collision series of pictures. So this will be before, and this will be after, like this. So before, after, there's Y and X, like that. Little Batman effect there. Okay, and so here initially, like I said, we have M2 going to the right with a velocity of v2 naught, and we have M1 that's at rest with a velocity of 0. All right. After the collision, we have M1 flying up this way with an angle of theta 1. And then we have theta 2 down here. We also know, whoops, it should be 1. The velocity here, and we're trying to find the velocity here. Okay, so if I were to use these pictures right here to look at what the initial and the final momentum is going to look like from an equational form, my initial momentum, P naught, which would be, M1 V1 naught plus M2 V2 naught, really just looks like this. And that's because our initial velocity for M1 is 0. So this, whatever this is going to be the total momentum overall. So after the collision, we have M1 V1 vector plus M2 V2 vector. And these vectors are going to be equal to each other. So if you put them equal to each other, what that says is that M2 V2 naught vector is equal to M1 V1 vector plus M2 V2 vector. Now, unlike the previous examples we've worked, here, these are, full two-dimensional vectors. So we can talk about what goes on in the x direction, and we can also talk about what goes on in the y direction. So sort of like how we treat forces. And that's exactly what I'm going to do here. If I look before my collision here, my momentum is entirely along the x direction, which means that if you look at the left-hand side, this is just M2 V2 naught, okay, and it's positive. All right. Now after the collision, both M1 and M2, let me put M2 here. Both M1 and M2, they have positive x parts. So you're going to have after the collision M1 V1x plus an M2 V2x. And we'll have to find these. So, or at least the form for them. Now, in the y direction before, though, there is no momentum. So after the collision along the y direction, our final momentum needs to maintain that characteristic. So what that means is if you look at my picture, V1 has a positive up, like it's a positive y direction momentum, but V2 is going to have a negative. So this would be M1 V1y minus M2 V2y. Okay, and now, just like we've done in the past for forces, since this is a vector, we're going to break these things up into components. Okay, so this will be theta 1, this will be theta 2. This is V1, this is V2. And, using opposite adjacents and hypotenuse, and noting the fact that this is V1y, and this is V1x, this right here, this would be V2x, and this is V2y. What this tells me is that v1x is going to equal to v1 times cosine of theta 1. v1y is equal to v1 times sine of theta 1. This also tells me that v2x is equal to v2 times cosine of theta 2. And v2y is equal to v2 times sine of theta 2. All right, so let's just take this stuff and plug it into these equations right here. If I do it to the top equation, I have m2 v2 naught is equal to m1 times v1x. Now v1x is this. Plus, I have m2 v2x. All right, so there's that equation. Now this equation right here says m1 v1y. So m1 v1 sine of theta 1 minus m2 v2y. And v2y is v2 sine of theta 2. Now we're trying to find v2 as a vector. So we need its magnitude in its direction. And what I propose to do in order to make our lives quote unquote easy when we deal with this is to put everything dealing with v2 on one side and everything that deals with the v1 on the other side and the initial stuff. So we'll start with this equation right here. This equation right here, and I'll write it over here, says that m2 v2 sine of theta 2 is equal to m1 v1 sine of theta 1. Now I know theta 1, v1, m1. I also know m2. What I don't know is v2 and sine of theta 2. So now I'm going to take this and, again, I'm going to take and put everything that deals with m2, v2 stuff, cosine theta 2, I'm going to put that on one side and then, move everything else to the other side. So when I do that, I get, using this equation right here, I get m2 v2 cosine of theta 2 is equal to m2 v2 naught minus m1 v1 cosine of theta 1. Now, you might be asking yourself, why are we doing this? Well, look, we have two equations and two unknowns, but one of those unknowns is tied up in the trig function. So what I'm trying to do here is to extract information out of that. And I'm going to do it by basically dividing the sides of these equations by each other, like that. So, m2, v2 sine of theta 2 divided by m2 v2 cosine of theta 2 would be the same thing as m1 v1 sine of theta 1 divided by m2 v2 naught minus m1 v1 cosine of theta 1. Now take a look here. On the left-hand side, these cancel, giving us only stuff that deals with our angles. And I know what sine over cosine is. This is going to be tangent of theta 2. All right. Now, what I also propose to do over here on the right-hand side, just to sort of maybe clean things up a touch, is to, let's see, what's the easiest way to do this? Maybe not. I think we'll leave it how it is. You can reduce this algebraically a little bit, but I'm not sure that it necessarily makes your life easier. So basically what this says, though, is that tangent of theta 2 is equal to m1 v1 sine of theta 1 divided by m2 v2 naught minus m1 v1 cosine of theta 1. Here's the deal. We know everything here on the right-hand side. We know all this stuff. And really all we're trying to do is to find theta 2, which means that theta 2 is going to be the arctangent of this right here. So if you take and you plug stuff in, and let me go up here real quick, and I'm going to snag this information right here. And let's go back down over here, and I want to paste it here just so we have something we can reference. So here, M1 is 0.16 kilograms. V1 is 3.0 meters per second. We have sine of theta 1. Theta 1 is 35 degrees. And then we're dividing this by M2 V2 naught. So M2 is 0.17 kilograms. V2 naught is 2.5 meters per second minus M1 V1 cosine of theta 1. So this right here is what we're dividing. So let me stick this into my calculator here real quick. Excuse me. The arctangent of 0.16 times 3 times sine of 35 divided by 0.17 times 2.5 minus 0.16 times 3 times cosine of 35. And I get 83.4 degrees. Now we want to remember this because now that we have the angle, we can use one of these equations here to very easily find V2. And I propose that we take and we use this one right here. So let me just sort of snag that real quick. And I'll put it over here. So this is what I want to manipulate just to solve for V2. And to do that, I'm just going to divide both sides by M2 and sine of theta 2. And let's just plug our stuff in. M1, 0.16 kilograms. V1, 3.0 meters per second. Sine of theta 1. Theta 1's 35 degrees. Divided by M2. M2 is 0.17 kilograms. And we have sine of theta 2. Theta 2 is 83.4 degrees. Okay. And so let's see what you get here. 0.1, let's see. Let's do it this way. 0.16 times 3 times sine of 35 divided by 0.17 times sine of 83.4. And I get 1.63 meters per second. Now, there's your velocity. So overall, we would write our velocity to, if you look here, it looks like 2 sig figs overall. Okay. So V2 is going to be 1.63 meters per second, making an angle of 83 degrees. Wow. Let me put this 2 sig figs actually there. Below x. And there's your final velocity. Now, we were able to do this because, again, being able to solve along y gave us enough information to be able to deal with it, especially knowing the final velocity of one of these. Now, in the situation that, maybe you had one less bit of information, like, for example, maybe I didn't know what V1 was. I knew what the angle was, but I didn't know what V1 was. Then what you'd have to do would be to also invoke conservation of energy. And that may or may not be easy. But at least from there, you can work through and you have an additional equation that gives you information. So then you would have 3 equations and 3 unknowns. We're not going to do an example that deals with that. So here's another example. A satellite of mass m explodes into 3 pieces, 2 of which have masses of 1/5 m and travel away from the debris with equal angles of 45 degrees. The third piece travels straight away with a speed of 120 meters per second. I want to know what the velocities of the smaller pieces are. So if I were to sort of draw this like as follows. So here's before. And then here's after. So here's our satellite. Sitting there at the origin. And then when it explodes, what happens is you'll have a piece that goes this way, a piece that goes this way, and then a piece that goes this way. Okay? So, whoops. Get rid of the shade there. So here, this is going to be 45 degrees for this piece. This will be 45 degrees for this piece. And this one is going to have to travel this way. Now, how do I know it's going to have to travel backwards if it travels square away? We'll take a look. If these guys are flying away with equal angles like this, their momentum is this way. We're going to need momentum this way to balance things out. Because if I look here, if this thing is at rest, then that means that that your initial momentum is 0. Okay. So I'm going to call this angle right here. This is theta. This is theta. I'm going to call this M1. This is M2, and this is M3. And this right here is capital M. So this is before. Then blam. There's your Batman effect. And then it goes to this. This is what happens after. Okay. Now, so what we know is this. We're given that the initial mass of our satellite is m. So if you think about it, M1 and M2 both have the same mass. So M1 is 1/5 of m. M2 is 1/5 of m. Together, this is 2/5, which means that M3, in order to account for the rest of the mass, is going to have to be 3/5 m. Okay, so that takes care of 1 m overall. We also know that our angle here is 45 degrees. We know too that our third piece flies away with a velocity of 120 meters per second in the minus x hat direction. All right. We also know that the initial velocity of our mass, which I'm going to call just v naught, is 0. What are we trying to find? Well, if we call this m1 and this m2, I'm going to call this v1 and this v2. And that's what we want to find, v1 and v2. So what happens before? Well, my initial momentum, which would be big M times v naught, is 0. After, though, I have three objects. I have m1 v1 plus m2 v2 plus m3 v3. And these are equal to each other. Okay, which means that, as per conservation of momentum, m1 v1 plus m2 v2 plus m3 v3 is equal to 0. So again, if I look at what's going on in the x direction and in the y direction, in x, I have m3 moving to the left, so it's going to have a negative velocity. But I also have v1 and v2 with positive components. Okay, so what that means is if I write in magnitudes, minus m1 v1 plus m2 v2x plus m3 v3x, that's going to equal to 0. Now in the y direction, if I take a look here, I have no part of v3, but I have a positive part of v1 and a negative part of v2. So that would be m1 v1x minus, not x rather, but y, minus m2 v2y is equal to 0. Now let's take and break our things up into components. Now the angles are the same. All right. So if you think of this, we'll say as v1, this would be v1y, and this would be v1x. And v1y is going to be v1 times sine of theta. v1x is going to be v1 times cosine of theta. Now, if I flip this and I look at v2, it's going to be the same for that. v2y is going to be v2 sine of theta, and v2x is going to be v2 cosine of theta. Now, so what I'd like to do to begin with is to plug stuff into Vy, or into what's going on in the y direction rather, because that's going to tell us something. Now watch. M1 V1y. I'll tell you what. Let's go ahead and plug in, instead of M1, let's plug in what M1 is. One-fifth of M times V1y. V1y is V1 sine of theta. Minus, now what is M2? Well, M2 has the same mass as M1. 1/5 M V2 sine of theta That's going to equal to 0. Those cancel. Those cancel. The angles are the same. Those cancel. So what this tells us is that v1 minus v2 is equal to 0, or the same velocity, or at least in magnitude. So v1 and v2 are going to be the same. I'm going to call this v. Okay, so that actually makes things a lot easier, because what that means is that if I were to take a look at this equation right here, okay, if I were to look at this equation right here, I'd have minus m1 v1. Now m1, actually it shouldn't be minus m1. That should be, okay, so found a mistake here. You guys might want to correct this. Sorry about that. Because this is 3. This should be 3 right there. And this should be 1. Like that. Yeah, sorry about that. That happens. Because it's 3 that's going back the other way. There we go. That looks better. Okay, so M3 here is 3/5 capital M. V3 is just V3. Plus M2 V2x. V2x is V2 cosine of theta, but V2 and V1 are the same. I'm just going to call that V cosine of theta plus M1. Again, V cosine of theta. That's equal to 0. And take a look. M's cancel. 1/5 plus 1/5 is 2/5. All right. And the fifths cancel. All right. And now we just solve for V. So V here is going to equal to 3 times V3 divided by 2 times cosine of theta. 3 times V3. V3 came from up over here. It was 120 meters per second. Why isn't it negative? Because we've already taken into account direction. 2 times cosine of 45. So if you plug this into your calculator, so cosine of 45, you get 169.7. So here we have what amounts to 2 sig figs, because 1/5 is an exact number. So 2 sig figs, 2 sig figs. This would be 170 meters per second. So what that says is that both V1 and V2. V1 would be 170 meters per second, making an angle of 45 degrees above the x-axis. And V2 is going to be 170 meters per second, making an angle of 45 degrees below the x-axis. And there you go. There's your answer. So, as you can see, two-dimensional stuff is a lot of times is a lot easier just because you have that extra dimension that you can access. Now, what do you do about situations in which both of these things are moving at a velocity and they collide? So let's just have a brief conversation about a situation like that. So let's pretend, just for a moment, that you had, I don't know, Whoops, get rid of that. You had maybe M1 traveling this way. Like that. And maybe M2 is traveling this way. Okay? So you could deal with the velocities as is, which actually makes a little bit more work for yourself than what you want to do. Or you can put yourself into a frame in which one of their velocities is equal to 0. So, for example, if I took and I subtracted away v1 naught from both of these, what that would do would be to bring this one to rest and then take and change this one's velocity. But you don't change the physics of the collision. It still happens. You still get angles before and after. Okay? Now, so when you work the problem, then what you do is you add that V1 naught back in. Now, I mentioned this, I believe, last time. So what that does is to take you into a reference frame, we say, in which one of them is at rest. You do your collision, and then you add V1 naught back into things once you get your final velocities, and that makes your life easy. Okay? Now, that said, though, if you subtract away V1 naught, you're going to have to do the same thing if you're given information about what's happened after the collision. Okay, you're going to have to do it to that as well. Now, what if you have a situation where you have things colliding like this? Well, one thing you can do is also rotate your coordinate system after you do your vector subtraction to put one explicitly along the x direction. Now, we know we can do that. We've done this multiple times. We've done this, for example, when we work inclined plane problems. So by rotating coordinate systems and by adding or subtracting velocities, you can always find a frame in which your complicated collision has one of the objects moving explicitly along x and the other one being at rest. And what that does is to make your collision problem look more along the lines of something like this, or potentially something like this, as opposed to something that's a big nasty kludge. Okay? So I don't want to get further into this except to say that this is what you would do if you were to go further on in the physics sequence. You would study things like this extensively. Doing collision problems and classical mechanics, which would be the next big class that you would take after this. Depending. So that said, the next big topic that I'd like to get into, which I'm going to introduce you to, we're going to do one or two examples with, but we're going to do far more examples with it when we talk about rotational motion, which is going to be the next big subject, is something called center of mass. Now, up to this point, everything that we've dealt with has been objects with no internal structure. So, for example, these masses that are colliding, we don't talk about physically how big they are. We just talk about how much mass they have. And for all intents and purposes, they act like little points that move around. Even when you do problems where you have things hanging by cables and strings and stuff, those things that are hanging are points. But in truth, these things have internal structure. They're not a point in space. They have dimensionality to it. And what that does is to complicate matters. For example, if you have a collision problem in which something hits something head on, the physics acts a lot like this. But now, if you have a collision problem where it hits it head on, actually at an angle above, we say this is an impact parameter. Then the behavior might be different than if it hit here or if it hit here. Okay? So when you add internal structure into things, what that does is to make your problem more complicated, but it also makes it more realistic. And the step to getting there is to introduce the center of mass. So, that said, instead of thinking of one object as being a point in space, I want you to think of an object as being a whole bunch of little masses that are attached to each other or bound to each other somehow. Maybe the thing has a total mass of big M, and it's moving to the right, we'll say, with a velocity of big V. So in a situation like this, we could say that your momentum, which I'll call capital P, would be big M times V. And in this situation, your problems that we've worked all back here, all the way up to the beginning of the semester, things work the same, the physics works the same, all that. But in reality, what you have here is one big P that's made up of a whole bunch of smaller ones. So each one of these little masses right here have their own individual mass, their own individual velocities, and so on. But it must be true that if I were to add up all of those individual masses and their individual velocities, okay, if I were to do that, I should get the original back. All right. So even though your object is made up of a whole bunch of smaller masses, when you add up their momenta, you should get the momentum of the whole object. All right. Now, that said, V, we know, is an object's position with respect to time. Okay, so we know that's the relationship there. Or d by dt of r. Now, what I'd like to do is to take this equation right here and pull this over here to the right-hand side. Oops. There. Like this. And I'm going to also assume that our masses in this particular situation are constant. Okay. Why would I assume that? Well, let's pretend one of these things is shedding mass. Well, now what I've done is to take and create a whole bunch of smaller masses with their own individual velocities. And if I add those up, I'm still going to get the original momentum back. So it's not an unreasonable approximation to say, or an unreasonable statement rather, because it's not even an approximation, to say that our mass here is constant. Because even if one of these things was shedding mass, like I said, you still do the sum and add it up, and those individual little bits of mass would be constant. Okay? So what that means is that this term right here, I can rewrite as the change in big R position over time. This term right here, I can write as the derivative of little position with respect to time. These are the positions of all the individual particles, and that's equal to 0. Now what I'm going to pull out, and what I'm going to do is to pull out the d by dt. Since the masses are constant, I can do that. Okay. Now, look, let's just take a look at this right here. Okay. This relates the position of the object itself to the positions of the little bits that make it up. Okay. So in order to find a clear relationship between big R and the little r's, what I'm going to do is this. Because we know this is true. It's got to be. I'm going to divide both sides by capital M. Now, this right here is called the center of mass. This is the point inside an object that follows all of these convenient laws. This is the point inside an object that were you to fire it through the air, it follows a parabola. Okay? This is the point inside an object that when you are summing up all the forces to look at how the object's mass experiences acceleration, that's the thing that's experienced acceleration. And you can actually visualize it pretty easily. If you take something like a remote to a TV or something like that, and you sort of toss it up in the air and give it a little bit of a flip and let it rotate, the point on the inside that that object rotates about, that's the center of mass. And this is how you find it. Okay. Now, this is the discrete form. Okay. By discrete, I mean that you're dealing with each individual bit as though they're individual bits. On the other hand, we know that we can also appeal to calculus a lot of times to help us find stuff. And another way that you can write down the center of mass from a calculus standpoint is to integrate from, we'll say, 0 to m, all right, r sub I dm. Okay, so this is the integral form. And this right here is the discrete form. So just as an example, I'm going to use the discrete form right here to find the center of mass of the system, right? So find the center of mass if m1 is equal to 5 kilograms at x is equal to 0, y is equal to 2 meters. This is x, this is y, and this is x, and this is y. Okay? So this would be x1, y1, this would be x2, y2, and this would be x3, y3. So typically what you do is instead of necessarily dealing with the vector form, is you just look at the components. So for example, the big x position would be what you get when you take and you add up, in this case from 0 to 3, or 1 to 3 rather, mixi, okay? The y part would be what you get when you do the same over y. The z part would be what you get when you do the same over z. Okay, and let's not forget you have to divide by the total mass. So for here, the total mass is what you get when you just sum up the masses. That would be 5 kilograms plus 2 kilograms plus 10. Well, 5 plus 2 is 7, plus 10 is 17. Okay. So in each situation here, we'd be dividing stuff by 17 kilograms. So let's do the x position first. X is what you get when you take and you sum up from 1 to 3 in this case, mixi, and then you divide it by the total mass. So this would be m1 x1 plus m2 x2 plus m3 x3 over big M. X1 is 0, x2 is 0, and x3 is 4 meters. M3, 10 kilograms. X3, 4 meters. And then you're dividing by 17 kilograms. So what is the x position of the center of mass? .35 meters. So from an x standpoint, it would be, since these squares will sort of scale, 2.35 would be somewhere around here for x. Now what about the y position? Well, it's the same thing. Okay, for the y position, you sum up from I is equal to 1 to 3. Again, in this particular case, mi, yi, and then you divide it by the total mass. That's going to be m1 y1 plus m2 y2 plus m3 y3, and then divide it by m, capital M. So m1 is 5 kilograms. Y1 is 2 meters. M2, 2 kilograms. Y2 is minus 1 meter. M3, 10 kilograms. Y3 is 1 meter. And then you divide again by 17 kilograms. So if I do this, I end up with minus 2 plus 10, then divide that by 17. That ends up being about 1.06. So from scale standpoint here, it's going to be somewhere around here. This is where the center of mass would be. So it's this point in space that, like I said, traces out the parabola when it flies through the air. Okay. Now, so that's it. We have a brief introduction into two-dimensional collisions, plus a little bit of center of mass stuff. I'm not going to do an example dealing with an object that has a continuous mass. Your book does a pretty good example, just showing how it works. But we are going to talk more about that when we move later on into rotational motion and talk about the rotational analog to mass called the moment of inertia. So you'll see plenty of examples there. But this is mainly just to introduce you to the concept because we'll be using it a lot in the future. And that's it.